Dear viewers, welcome to case study on aircraft jet engine analysis by finite element analysis. In this video, we are going to see structural analysis of aircraft jet engine. A jet engine is a type of reaction engine discharging a fast moving jet of heated gas, usually air, that generates thrust by jet propulsion. Finite element analysis is now widely used in complex problem solving in the following areas: structural strength design, structural interaction with fluid flow, shock analysis, acoustics, thermal analysis, vibration, crash simulation, fluid flow, electrical analysis, buckling problems, dynamic analysis, electromagnetic evaluation, and metal forming analysis. The simulation is shows the various pressure region. The color indicate the low pressure shaft. Another reason is high pressure shaft and other structural component of aircraft jet engine. The aircraft jet engine analysis finite element analysis. The first step, we have to create a geometrical modeling of in aircraft jet engine components. The component part of a jet engine are inlet. The gas turbine engine consists of compressor, a combustion chamber, and a turbine and the exact nozzle. Air is drawn into the engine through the inlet and compressed and heated by the compressor. Geometrical modeling of jet engine components. It involves creating accurate digital representation of various components within the jet engine using specialized computer design CAD software. This process enables engineers and designers to visualize, analyze, and optimize the component before they are physically manufactured, leading to more efficient and reliable engines. The key components that are commonly modeled in jet engines: fan and compressor blades and a combustion chamber. Fan and compressor blade generating the necessary air flow for engine operation. Geometric modeling of these blades involves defining their shape, curvature, airfoil profiles, and the number of stages in the compressor. Optimization techniques help engineers achieve the most efficient aerodynamic design for improved performance. Combustion chamber, fuel is mixed with air and ignited, generating high temperature, high pressure gases to drive the turbine. Modeling the combustion chamber involves creating the complex geometry of the liner, igniters, and fuel injection system, ensuring optimum fuel air mixing and combustion efficiency. The next key component of aircraft jet engine: turbine blades and nozzle and exhaust core. They extract energy from the hot gases produced in the combustion chamber, driving the engine core and fan. It includes defining the plate profiles, cooling channels, and material property to withstand the extreme temperatures. Nozzle and exhaust cone responsible for, responsible for accelerating the exhaust gases and converting thermal energy into propulsive force. Modeling this component involves considering the shape, expansion ratio, and optimization to maximize the thrust while minimizing the noise and emissions. The next key component of aircraft jet engine, bearing and shaft assemblies. Jet engine consists of several rotating parts, including shaft and bearings. Geometric modeling ensures the proper alignment and fit of this component, minimize the friction, vibration, and allowing smooth rotation with minimal losses. Casing and cowling. It protects the engine component from external forces and provide aerodynamic shapes to reduce the drag. Modeling these structures involves creating a seamless outer surface while considering access point for maintenance and repair. The next key component of aircraft jet engine, inlet and outlet ducts. Geometric modeling of inlet and outlet ducts is essential for optimization airflow into and out of the engine. The design should reduce the pressure losses, prevent incorporation of foreign objects, and improve overall engine performance. Support structures. Jet engine are mounted to aircraft wing or fuselage through support structures. Modeling these structures ensure the proper alignment and distribution load to maintain the engine's structural integrity. The next step, we have to identify the selection choice of the material. Then we have to specify the material property. So normally in aircraft jet engine component using aluminum, titanium, nickel based alloys. The selection of the material is very important for aircraft jet engine component. For their component is crucial to ensure their efficiency, performance, and durability under extreme operating conditions. The choice of material depends upon various factors, including temperature, pressures, mechanical stresses, and specific role of each component within the engine. The following material used in aircraft jet engine component. One is nickel based superalloys used in the high temperature section of jet engines such as turbine blades and disc exhibit excellent creep resistance. It gives high temperature strength and resistance to thermal fatigue. Nickel based superalloy withstand the extremely hot gases in combustion chamber and turbine sections. Another material used in aircraft jet engine is titanium alloys. It employed in the part of engine exposed to both high temperature and mechanical stresses such as compressor blades and casing. Titanium offer a good strength to weight ratio, corrosion resistance, and retain its mechanical properties at elevated temperatures. The another material used in aircraft engine components is cobalt based superalloys and ceramic matrix composite materials. Cobalt based superalloy used in specific applications in the region of high temperature and corrosion such as the hot section of some turbine engines. It provides excellent resistance to oxidation and cut corrosions. Ceramic matrix composite. It consists of ceramic fiber embedded in a ceramic matrix offering exponential thermal and mechanical property at a high temperature. Ceramic matrix composite are being explored for turbine surround and combustor liners to improve fuel efficiency and reduce the engine weight. Another material used in aircraft jet engine is stainless steel and aluminum alloys. Stainless steel exposed to high temperature gases and corrosive environment such as exhaust nozzles, some section of combustion chamber. It provides good resistance to oxidation and corrosion. Aluminum alloy used in low temperature component such as the engine casing, some part of compressors. Aluminum alloy have good balance between strength, weight and cost effectiveness. Another material used in aircraft jet engine component, single crystal alloys. Single crystal alloys, modern jet engine, single crystal alloys are used for turbine blades. It have unique microstructure with aligned grain boundaries, providing superior grip resistance and mechanical strength. Carbon composite employed in jet engine component requiring high thermal conductivity and low thermal expansion such as thermal protection system and nozzle threads. Refractory metals like tungsten, molybdenum are used in certain specialized applications such as igniters and high temperature electrical conduct. The next step of finite element analysis, creating a discretization approach, it is called mesh generation. The aircraft jet engine analysis and simulation meshing refer to the process of dividing the complex geometry of engine component into smaller interconnected element called mesh cells. The mesh process involves the following steps: geometry import from other CAD packages, pre-processing, mesh generation, boundary layer meshing, refine or adaptive meshing and grading, quality checking and mesh independent study, expertise mesh to simulation software for analyzing of structural analysis or thermal analysis. Aircraft jet engine component based on the accuracy, we can use the 2D element or use of 3D FEA element. Actually, 2D element used for aircraft fuselage and wing skins. The 3D element used in engine components. Aircraft jet engine structural analysis to ensure that the engine can withstand the load, pressure, and temperature it experienced during the flight while maintaining its structural integrity and avoiding failures. So actually, the structural analysis, the aircraft will be having various parts with various pneumatic powers, electrical powers, hydraulic powers, mechanical power component. The aircraft jet engine structural analysis involved in the following steps: finite element modeling, boundary condition, material property of engine components, static analysis, thermal analysis, fatigue analysis, dynamic analysis, failure analysis, optimization based on the analysis inference. The structural analysis of aircraft jet engine typically involves the following steps: finite element modeling. The first step to create a finite element model of engine component using specialized CAD softwares. The 3D CAD model is divided into a smaller element. It's called discretization approach. It's called finite element interconnected at nodal points. Each element shows a specific region of the component of geometry. The next step specify the material property of aircraft engine component. Material property of engine components such as Young's modulus, Poisson ratio, thermal expansion coefficient, and yield strength are assigned to the corresponding element in finite element method. The material property define how the material is respond to mechanical and thermal loads. The next step assign the specify the boundary condition of the aircraft jet engine components. Boundary conditions are applied to the model to simulate the engine's real world operating condition. It includes loads, pressures, thermal variations, and constraints that the engine experience during the different flight phases. Static analysis of the aircraft jet engine assembly. Static structural analysis determine the engine's behavior under steady state loads and determine stress distribution, deformation, and a factor of safety. Aircraft engineers can identify the region of high stress concentration and potential failure points. The structural analysis of aircraft jet engine major point is dynamic analysis. Dynamic structural analysis assesses the engine's response to dynamic loads such as vibration or forces generating during engine startup or in flight maneuvers. This analysis helps ensure the engine component do not resonate at critical frequency. Analysis. Thermal structural analysis study the thermal behavior of engine components. It accounts for temperature distribution, thermal stresses induced during the engine operation, especially in high temperature region like the combustion chamber and turbine. The next analysis, fatigue analysis. Fatigue analysis evaluate the engine component under cyclic loading, which is common during the operation like an aircraft. It predicts the accumulation of the fatigue damage and help determine the component fatigue life. Failure analysis. In the event of an engine failure or an anomaly observed during the testing or service, failure analysis is performed to investigate the root causes of the failure. The failure analysis involves examining the structural behavior, material properties, and loading condition to determine the failure mechanism. Based on the structural analysis of aircraft jet engine components, it is a important conclusive inference is optimization. Optimization based on the analysis result, engineers may explore design modification or material changes to optimize the engine performance, weight, and durability. The next important of this analysis is certification and compliance. Structural analysis is essential part of certification process for aircraft engine. This analysis result are compared to the industry and regulatory standard to ensure the compliance with the safety and performance of the aircraft engine components requirement. The aircraft jet engine analysis, stress and strain analysis is important. So, stress and strain analysis will involve combined load analysis. In real world scenario, engine component may experience a combination of mechanical and thermal loads simultaneously. The combined load of mechanical and thermal analysis evaluate the effect of both mechanical and thermal stress to ensure the structural integrity of the aircraft jet engine components. The next analysis, buckling analysis. Buckling analysis is conducted to assess the stability of the cylinder of aircraft jet engine component such as turbine blades and soft under compressive loads. It ensures that components do not buckle or deform under critical operating conditions. The next, automation and design improvement. Based on the analysis result, engineer can optimize the design of engine component, introduce reinforcement, or make material changes to enhance structural integrity and safety. In this video, we are seeing that summary of aircraft jet engine analysis by finite element methods. First, we have to identify the aircraft jet engine component, geometrical shape, profile, aerofoil, creating a geometrical shape by using CAD software. Then discretization approach, meshing, then material property, assign the boundary condition, then discussed various analysis of structural analysis of aircraft jet engines part 1. The next video we can see the thermal analysis of aircraft jet engine, the next video. Thank you for watching my video. We can see the next video of part 2 in thermal analysis of aircraft jet engine. Thank you.